If you want to understand the Fourier and Laplace transforms, then this is a book you want to buy. The book that I'm going to review today is probably my all-time favourite book on a technical subject of signals and systems. So this is called Transforms in Signals and Systems by Peter Kraniauskas. I bought this back in 1992, I think I bought it, and I was between my second and third year at university, and I was wanting to try and get a better understanding of the Fourier and Laplace transforms, and I was struggling a little bit. It was okay actually doing the questions, but understanding what I was doing was difficult. So this is the first book review I've got here together, and you'll notice I've got my image up at the top of the screen here, a little bit whited out, but that's because I've got a lamp here just shining down in the book, and it kind of shines back in my face. But let's get started on this book. This is a graphical 3D representation or interpretation of the area of the Fourier Laplace transforms and also of the discrete and Z transforms. So I'm just going to flick through a few pages here just to get you started till you see what's in it. So we'll start off here with the contents. Now I'll just quickly flick through to show you the contents here. So we're going to have a chapter 1 here, which is Signals and Systems, the Physical Phenomena, the Fourier Series, Introduction to Transforms, Complex Variables, Fourier Series Exponential Form, and we've got this chapter 2 which covers the Fourier Transform. So that's the Fourier Series to the Fourier Transform, Graphical Interpretation and Developments, Transform of General Complex Function, Transform Properties, and then it goes on to the Laplace Transform. So it goes on to the Laplace Transform as an extension of the Fourier Transform, the Inverse Transform, Poles and Zeros in regions of convergence, Function Symmetries, Transform Properties, Unilateral Laplace Transform, and then it goes on to the system description. So I'll leave you and you can read through the contents here, or you can also pause the video if you want as well, obviously, to read through some of these. So again, it's covering the next system. Next section is a systems solution, so you can read through here. I think you can see that okay. Now, part 2 then covers the same material that it covered in part 2, but it covers it for discrete systems. So we then go through the discrete classes of the transforms. So we go through sampling and reciprocity, discrete time, discrete frequency, discrete time and discrete frequency, and the summary and interpretation of what we've learned here, and the Fourier interpretation of a function. And it goes on here to look at the discrete Laplace transform and Z transform. So it's really just the taking the Laplace transform and making it discrete, which is really the Z transform. And then it looks at the Z transform, poles and zeros, transform properties, a unilateral transform, transform interpretations. And again, there's another chapter here on the system description for the discrete systems, and also the systems solution as a chapter here, chapter 9. And then finally, it goes on to the system synthesis. So it's really how to synthesize continuous and discrete systems. So we've got ideal and realized continuous time systems, and I'll leave you can read down through those there. And so it's really all about a system and filter design for discrete and continuous systems. So it's really using that as examples of how the mathematics and the graphical representations then get used in actual real life situations. Okay, and the same thing for generating discrete time systems and system simulation. So quite a lot involved in the book there, and it does have how many pages? About 550 pages, and it's quite large typescript as well. Okay, so let's go through and we'll start really in the first chapter here, and it's an introduction to systems and signals and systems. But the main point about this is that the entire book is really worked through in a graphical format here. And you can see that the graphical format's continuing here. We're looking at a continuous aperiodic function, a continuous periodic function, a discrete aperiodic function, and a discrete periodic function. So all the way through the books it does use the actual drawings here. But of course it covers it all graphically. So we've got a section on convolution. So this is how you would normally cover convolution if you were learning it at a college or university somewhere. But he's actually taken the entire idea here and he's created it or described it in a three-dimensional sense. So the dummy variable tau, which is a time variable, is drawn along one axis, and the actual time variable is drawn along the other axis. And he draws out the convolution in a 3D manner, and whenever you see it drawn out 3D, it's actually quite easy to see how the dummy variable tau occurs and where it is and how it's associated with the actual time variable. So that there was beautiful for me way back in 1992, 93, and it gave me a real aha moment when I seen it drawn out in 3D like this. And this is what attracted me to this book. I think I was in James Thin bookshop in Edinburgh. I don't think it's there anymore. And when I opened it up and I just flicked through and I seen this, and then instantly I seen this, I just clicked and I thought, yeah, I understand that now. I can see where this is coming from. And as I flicked through the book, it was beautiful. You know, it was just fantastic. And I managed to pick it up just at the beginning of a few months break that I had, and I worked through this entire book in that few months. So again, there's an awful lot of the mathematics here as well, and a graphical representation of how we generate the Dirac delta or the impulse function. So it can be generated by any even function. So that's generated by a simple even square function, and it's generated by a triangular function. And it goes through the basics of trigonometry, and we can see basic trigonometry here. But again, everything is drawn out in a 3D approach. So here's a basic idea of generating a function using a summation of sinusoidal functions of varying frequency and varying amplitude, and it's drawn out in a 3D approach, and you can see the actual individual phasors drawn out here as well. So the whole point here is at the very beginning, from the very beginning, it creates a roadmap or a route through from a time domain through some surface to a frequency domain. So we have time and we have a frequency, and we have the mapping from the time to the frequency, or the frequency to the time, via some surface here, which we haven't yet defined, but that gets defined through the book. But this is really the core part of how the entire Fourier and Laplace transforms are described within the book. Time to frequency through a surface, or frequency to time through a surface. And we've got here the inverse transform mathematically. And all the usual mathematics is there, you'll see at a college or university. But we've added all of the 3D representation. So here's a complex exponential here, which looks like a corkscrew. And if you look in from, say, the top angle, you're looking down at the imaginary part of this, and if you look in from at 90 degrees, you're looking at the real part. So you're looking at the sine, the I sine, and the cosine part of this corkscrew, which is your complex exponential, and then it shows you again rotating in the opposite direction. So again, a lot of these simulations, I've regenerated a lot of the simulations in MATLAB. In fact, I went through the book and generated as much as I could possibly that is in the book. It's all been redone in MATLAB because I put together a course on Fourier and Laplace transforms, and I based it on this approach, but I added in obviously some other stuff of my own. And again, we've got the generation actually of this is the complex Fourier series, and it's we're looking at individual parts of the complex Fourier series and how it is built up. And a little bit here, what graphical interpretation, time shifting, what happens when we shift a function in time, what happens to the frequency components, and it shows you here graphically again, and they're using this 3D approach. So we've got the time, we've got the frequency, we've got a surface here. In fact, in the surface in effect, we have a frequency axis down here, so you can see the frequency increasing, and we've got a time axis along here, and you can see that we're going to be generating this function here using these series of phasors. Okay, these phasors are represented in this surface, and you can see, for example, the phasor at the centre would be, in effect, in electrical engineering terms, would just be the DC term. And we've got the increasing frequencies here, and increasing frequencies in this direction. Okay, so in all these, as I say, it does it in a 3D approach. And what we do here in this instance here, we take this function here, and we're going to delay it. So whenever we delay it in time, it's equivalent to allowing these phasors to rotate. Okay, so this is the rotation of those phasors, and you've got it all drawn out in beautiful detail. Okay, so I want to continue along quite quickly because there's so much in the book and I don't want the video lasting for hours. So we go from the complex Fourier series, and then we move on to we will move on in this section here to looking at the derivation of the Fourier transform. So we look at the Fourier transform as taking our square function and increasing the period. So we increase the period over and over again, and there's a graphical representation of what that happens whenever we do that. It's this, okay, and this little drawing here is a nice little representation of a graphical representation of the extension of the Fourier series to the Fourier transform, and it's a nice graphical way of describing it. Okay, so again, that was a nice aha moment for me all those years ago. And we look at the inverse transform, Fourier inverse and forward and inverse transforms mathematically, and we're really starting here at this point here to start looking at it in terms of this surface. So in this instance here, we've got a purely even function of time, so we only need to map through one part of a surface here. Okay, so this would be cos omega t surface, this would be omega, this would be t, and we would have this function in this instance here that's actually the inverse. So we have this function here modulating that surface and then integrating in this direction to get back to the time domain signal. So we start at frequency. Frequency modulates a cos omega t surface. We integrate in this direction to get back to our time domain signal. But of course we can work through the opposite direction. We can go from the time domain and we can modulate the surface, and then we can integrate in this direction to get to our frequency domain. Okay, so this is the basic premise of the book and the core of what the book is all about time, surface to frequency, or frequency, surface to time. Okay, so, and you can see that we go through the properties of the Fourier transform, and it describes all of the main properties of the Fourier transform using this graphical approach. Now, I'm not going to talk through all of them here, but we'll be able to see a few of them that we're working through. Okay, so this is the generation of an impulse function. So an impulse function here in the time domain would be equivalent to the the entire frequency range and the frequency domain. So if this was infinitely narrow and infinitely high, then we would have the entire frequency range from plus to minus infinity. So it shows you this here, and again I've generated this in MATLAB and I've worked through in order to see the impulse function being generated, okay, from the sinc function. And again, looking at a time-lapse image here, okay, and we're looking at a delayed signal. See, there's a delayed impulse. So a delayed impulse in the time domain would take the brick wall, in effect, the brick wall filter here, and it would rotate every one of the phasors. So you would get this action here. So there rotates this. If I can bring it back through here, don't want to get through all this too much detail, but in effect, this here, all the phasors would start rotating whenever this signal here gets shifted to the left or right. And what we see over here is all of those phasors starting to rotate. So beautiful imagery, and it's well worth the price of this book, and you can get it online still. It's in, I think it's been reprinted a few times. So again, all the mathematics that you require and you would expect to see in a book on signals and systems. And again, working through looking at the purely even functions and purely odd functions, and functions that are a mixture of even and odd. If it was a mixture of even odd functions, then the e to the I omega t, e to the minus I omega t surface, you would be modulating both a cos omega t and an I sin omega t surface. So in effect, you would have two surfaces that you would be modulating. So it gets a little bit more complicated with functions that aren't purely even or aren't purely odd, but are a mixture of both. But it still shows you them graphically, and still very understandable and easy to understand. And that's what we've got shown here. There's an example here. You've got a function here of time, and this function here modulates. It's not neither even nor odd, it's a mixture of both. So it modulates a cos omega t surface. It also modulates a sin omega t surface. The cos omega t surface would generate the real part, and the sin omega t surface would generate the imaginary part. And in fact, actually, looking at this one here, you can see actually the real part is actually 0. So it's not, it's actually a purely odd function, this. Okay, so it's a purely odd function, so it's only got one surface. It's got this surface here that will actually produce an imaginary part, and this is what it produces here. And you can see that it's generated the actual magnitude and phase response of this time domain signal, all drawn out graphically. And again, other examples here of the same types of functions, and it works through graphically here as well, other transforms. So it literally goes through all of the main properties of the Fourier transform, but it goes through it in a fantastic graphical fashion that you just won't see anywhere else. Other than, of course, if you do my course on Fourier and Laplace transform, because I've used the same method in order to do this, and I've explained it all. This isn't actually a sell for my course, or a sell for the book. It's just me just telling you what I really find interesting. But I've generated all of this in MATLAB, and it does all work, and it all works beautifully, and it goes through the transform duality, and so an impulse. So if we find the Fourier transform, we get this here, and then if we Fourier transform this, we'll get this, and then if we get the inverse transform of this, we'll get back to this one here. Okay, so there's a duality here. You can see that this one here is the same as this, and this one here is the same as this. There's only a difference actually of 2 pi for each of these. And of course, I go through my course displaying, and it explains in this book where that difference of 2 pi comes in. Time and frequency shifting. So this is, and it's got convolution of functions as well. So, and also differentiation integration of what happens whenever you Fourier transform a derivative and Fourier transform an integral, and it gives the graphical representation of what happens whenever we do that. Okay, so that's pretty much that chapter. So loads and loads in it, and that's just one of the chapters of the book. Now the next one is the Laplace transforms, and what this is an extension of the Fourier transform. So it looks like the same graphical representation, but it represents it not as just a rotating phasor, but a rotating phasor which is actually going to be what's the right word? It's going to be decreasing, or it's going to be increasing. So you add this extra term in order to ensure that the integral converges. That's the right word I was looking for. So here we go again. It's the representation of rotating phasor, but not just rotating phasor. It's a rotating phasor, and it's got an amplitude modulation on it as well. And you can see here we're representing the imaginary part, which has got an amplitude modulation, and a real part with an amplitude modulation. And we can look and we can see that all of the different modulations and what happens for all of the different types of modulation. So fantastic representations here. Doesn't matter if you don't quite understand that just now, but if you buy the book and then you do a little bit of signals and systems, you will come to appreciate the beauty of what we have here. And it goes through the Laplace transform again in the same way that went through the Fourier transform. It goes through it in a graphical representation. The only difference now is we still have our two surfaces. We have a real and imaginary surface that we act through. The imaginary surface will create an imaginary part, and the real surface will create a real part. We have our function here which will modulate these surfaces, but before the function modulates the surface, the function itself gets modulated by this amplitude modulation. So let's say it's decreasing here. So this modulates that, and then this modulates both of these, and then we integrate in this direction to get the real imaginary part, and then we're going to have to take the real imaginary part and find what's the right term, the square the real, square the imaginary, take the square root, and we'll get the magnitude. That's the word I was looking for. We'll get the magnitude of the Fourier surface along this line, okay? But then we would have to shift this to another point, and then we would have to do the same. But we would do that continually all the way along here until we build up an entire Fourier surface. And we can see here it works through the same process, but in inverse, as an inverse transform. And so here's a graphical representation here. Again, some more graphical representations and bits about the poles and zeros and regions of convergence and where the poles are and how the poles are generated. And again here as well. And here we can see we've actually got the Laplace surface starting to be built up. Okay, so we're looking at a pole here, and we're looking at a zero down here. In fact, it's just a pole in this instance. So this is going to be the Laplace transform of this function here. So we're taking a Laplace transform of this function here, and we're getting a pole at the origin. Okay, I don't know if it's actually a pole at this point here. Okay, point A. So again, it's graphical. You need to have a look at yourself if you decide to buy the book, and it also goes through all of the main properties of the Laplace transform, and again it goes through it in a fantastic graphical detail. Okay, and I'll just flick through quickly here because we've still got a lot to go through. You can always pause this video and decide to come back to it at some time, so because I think it's going to be another 10 or 15 minutes to get through the rest of this book. Now, I'm not going to talk through the system description sections, but it goes through really the first and second order and higher order systems. Okay, and it talks about them in relation to our Fourier and Laplace transforms. And there's also a chapter 5 that goes over, which is that's chapter 4. There's also another chapter which goes over the systems, okay, and it's again another section, and everything's done, as I say, in these graphically. Okay, so it's really the kind of systems side of this here. Okay, now I'm not going to talk over that in any detail because I would be here the entire evening. There's so much in it. Now that's really the first half of the book. I'll try and speed up the rest of this here. We have the rest of the book, which is really the discrete representation of that. So what I think I'll do is I'll stop the video here. Okay, I'll maybe move that up so you can see my face with a face a little bit better. Okay, so I have my face a little bit better. So I think I'll stop the video here because it's going to get too long. This is my first book review, so obviously I have to understand I'm going to have to shorten it somewhat. But this is the first half. I think I'll leave it here and I'll go on to the second half and we'll flick through the second half, and it's the same type of stuff, but it's done in terms of discrete systems, and we go from the discrete time Laplace transform. We look at the discrete transforms, so discrete frequency, discrete time, discrete frequency and time, and then we look at the discrete Laplace transform, which in effect is the Z transform, and it kind of finishes up at the Z transform. So that's all for this book review. I hope you liked it, and I hope that if you're interested in signals and systems, you really want to get a mathematical and graphical detail as to how it all works, and really this is the book that you want to get.